All right, good afternoon. Hope you're having a good one. It is very, very warm here in the central United States. And just trying to stay cool and enjoy what I can of soccer. So today, we're continuing with essentials of compilation. We're going to get to register allocation, and I think that if I recall correctly, last time we read a little bit about it, and we're going to need to do some interesting things to the process that we had from previous chapters. So, in addition to the issues of heap allocation from the previous chapter, now we have to consider the call ABI and that boundary in register allocation. So it's going to be pretty interesting and potentially challenging. And one thing that we didn't do when we did chapter 3 over a year ago, this is a long time ago now. But one thing that we didn't do was the challenge about move biasing. So we may need to look at that today. But let's get started. Hopefully you all are having a good day. Let me make sure that's getting loose. My camera mount was getting a little bit loose. Okay, so let's get going. I also have, I'm not sure what we're going to do after chapter 7. I think like the chapter 8, which is about lexically scoped functions, is pretty interesting as a potential next bit, but we may also take a break like we did after chapter 6 and do something else. And I have an idea for a Gleam project that may be interesting, but it may also be not so useful. So we can maybe talk about that later in the stream. Again, if you're here and you are seeing difficulties with the like video or audio, please let me know. So we're gonna switch. All right. Hopefully I'm not too much in the way. Okay, so register allocation. The addition of functions requires some changes to all three aspects of register allocation, which we discuss in the following subsections. So we're going to have to refer again to that graph that's at the end of the chapter that shows the sequence of phases, and we'll have a look at that in a minute. So the first phase, liveness analysis. So we have to handle. Make sure that we've got the right stuff here. Okay, yep. We have to handle indirect call queue. So it should be treated like call queue regarding its written locations W. So, call queue writes to RAX, and we can look at that real quick. This is liveness analysis. What is the name of that phase? Is it build interference? No. Uncover live. I don't know why they didn't call this uncover live. Oh well. Okay, so this is referring to what are the read and the write locations in each instruction, right? Okay, so, call queue writes to RAX. Okay. Right, so recall the reason for that is to force, okay. They should include all the caller save registers. So, so we need to we probably need to adapt call queue and indirect call queue such that they treat all the caller save registers as written locations. Now, we could, so if we look at our x86 base here, we have the callee save registers and the caller save registers. Now, we could go and say, you know, obviously RAX, but like these are, these include the argument registers. Okay, well, if this fully subsumes the argument registers, then we probably need to just use this constant as part of the set. And I think that we weren't doing that before. Okay. And the reason we weren't doing it before is because the only thing you could call was readint, and readint takes no arguments. So, you know, we didn't care about the caller save registers. Maybe we should have. Yeah. Okay. Hi, Willie. Welcome back to the stream. Hope you're having a good day. Okay. So, recall that the reason for that is to force variables that are live across the function call to be assigned to callee save registers or to be spilled into the stack. So when we say that, we say the callee has to save and restore these registers. So that means that it's safe for these registers to be live across a call, but these are not safe to be live across the call. So the caller has to handle, I'm going to put these onto the stack, etc., or on the heap or whatever. They can do whatever they want there, but just know that this means that the function you call will or can make use of these registers, and one of the ways it makes use of those is that you know, they are argument registers. So, you know, they're a bit in a different order here. I think I did them in just an alphabetical order here, but you know, you have RDI, RSI, RDX, RCX, R8, and R9. You know, fully, you know, 6 of those are used for argument passing. RAX is used for the return value of a function. Hi, Renatias, welcome. R10 and R11, I'm not sure. This is just part of the Unix ABI, the POSIX ABI for x86. Okay. Right. So the variables that are live across the function call need to be assigned to either callee save registers or spilled onto the stack. Okay. So regarding the set of read locations, the arity fields of tail jump and indirect call queue determine how many of the argument passing registers should be considered as read by those instructions. Okay, so that makes sense. Also, the target field of tail jump and indirect call queue should be included in the set of read locations are. Okay, so because these are the way that they're structuring these function calls is put the address of the function in a register, and either you jump to it because it's a tail call, or you do the indirect call queue, which is like deref that register. Renatias. You know, I should listen to Telemundo quite a bit more, get my R's rolling better. Okay. Renatias. Anyway. Okay, so okay, well, I will do that. The target field, right? So we have to consider the variable, which will eventually become a register. It has to be a register at the time of the call. That has to be in the read locations. Okay, so let's dig into this. I think that we have enough to get started for Uncover Live. Okay, so let's go up to the top and do our usual dance. We're gonna make this x86 def call queue, and then we're gonna have to deal with the fact that these are, you know, defs. The interesting thing is, though, we kind of need a control flow graph per definition. Yep. And that makes sense because essentially before, our program was one function called by the runtime, basically. Yeah, Rena. It is, by the way, it has been super fun. At the times, you know, first we had to because of where we were. We didn't. We were on vacation. We were staying in a place that didn't have, you know, live local television channels. And while we're sitting here thinking about this, let me restart Zed. And so all we could get was streaming, and the streaming was Telemundo. So we watched, while we were on vacation, we watched a bunch of World Cup matches in Spanish, which was super fun. Mostly just like the enthusiasm of the commentators is way more than any, you know, American commentator would give. So, and there's one or two of the play-by-play announcers who like really roll their R's for emphasis, and it's hilarious. So, okay, getting off track there. We're gonna look at, right. So it's interesting that that's a graph from string to null. Oh, that's the edge has no, yeah. Okay, so that's just the node is a string and the edge is nil. Let's go to that. Right, so the weight, the key, yeah, okay. All right, so now that we have, let's make a few fixes here. Rather than this, let's make a fun uncover definition, live definition, and its input is going to be x86 definition, and its output is going to be x86 definition, and this is basically going to subsume what we had before. So we'll say new blocks, input blocks, and we'll do build CFG, and we'll do analyze data flow, input.blocks, and then we'll just copy this. Oh, I need to pipe. Okay, and then we'll go, this is x86.definition, input, and blocks is new blocks. So we're basically repeating what we had before. But now we can turn this into just a map. And this is going to be, we're just going to say, because now it's just x86.program only has definitions in it, right? Well, it has these things. And I think that probably what we need to do is move, like we talked about previously, we need to move some of these things into definition. Hey, welcome, Sid of Musics. Welcome to the stream. Yeah, so I think we're gonna uncover some issues here. Um, let's first comment that out, and then we're gonna say x86 program. Let's just do input like this, and the defs are gonna be list map input.defs uncover live definition. So there we're not changing any of the fields in there because we have the splat except for the definitions. So we've kind of moved it down here. Now we're going to uncover other problems, and I think that we need to be prepared for that. The big one being, I think they're used in later phases even, but you know, the conflicts, these all basically need to go in the definition. Because when we generate the prelude and conclusion for each definition, we need to know which callee save registers to save. We know how many stack variables to allocate, and how much we need to bump the root stack, which is for our heap, the root stack size. When I say it's for our heap, the root stack is a special area that we've allocated to be the roots of items on the heap. So yeah, and I think the conflicts, the interference graph, I think we'll see that. Let's look at what they say. Okay, right. We compute a separate interference graph for each function, not just for the whole program. So I think that when we... Did I make a new definition function? No. We'll have to go back and do that. Right. Okay, so let's focus on liveness analysis, and we will not worry yet about the sorry for my flipping so much. We will not worry yet about these things, but they are definitely going to go on to the definition, at which point the new program becomes much simpler, and we need to make... Here, we can just quickly find all references. So it's really only in select instructions that we call new program, but I think that what we need to do is have a new definition function and put the splat in there and only deal with the things that we are copying or modifying in this phase. So we'll go back and do that. All right. But first, let's deal with Uncover Live. Okay, so now that we've got those updated, we have a bunch of issues down here, and this is, we have instructions that we have not handled yet. So let's add the missing patterns, and then we can deal with each of those. So this is read locations. So arity fields of tail jump and indirect call queue. Yeah, the problem is we didn't put that on indirect call queue. So we're going to have to go back. And I think that we fought with this last time. We're like, do we keep propagating the types? And we may have to go back to earlier phases and make sure that whenever we have a function call, or we've turned something into a fun ref, that we wrap it with the has type so that we can propagate the arity through. Yeah. So we don't know. With the indirect call queue, we don't have that information. We do for tail jump. So let's at least get tail jump done, and then we can go back and fix the type issue, hopefully. So this is going to be... Right, so target field of tail jump should be included in the read locations. Right. Okay, so we're going to do set union of locations in arg for a label. And then we're going to take so set from list, and we'll say list take from x86 base dot argument registers. Alrighty. That's going to give us let's make a block here, and then it'll be easier, a little bit easier. Okay. And what we're going to do is we're going to pipe that. So let's take x86 base argument registers. We're going to list take arity, right? So we're getting up to the number of arguments. We're going to list map, and that's going to be, do I say location reg? Location reg. So we're wrapping that location in because we know they're registers. And then we'll say set from list. And then we'll union with this. So now we need to do the same thing for indirect call queue, but we don't have the arity on it. So we're going to have to go back and fix that. Now this one is straightforward, and it's just this, right? So okay. Before we address this to-do, let's do the same treatment for write locations, because they talk about that first, but we did the read ones first. All right. So again, we didn't address call queue arity. So all the caller save registers, we need to treat that so we looked at obviously return value of REX. So let's say this is we can treat these the same, but we're going to have to adjust them. So actually this is incorrect. B is not read from. This is more like move. Yeah, sorry. That was incorrect. I almost made a big mistake there. You're like, why is it a big mistake? Well, if this is wrong, then we can't allocate registers correctly. Okay, so again, this is like LEAQ is straightforward. This is locations in B. We'll need to figure out tail jump. But indirect call queue we need to fix. So let me split this to the bottom, and then we can look at it at the same time. So they say we need to include all the caller save registers. These will be written to. So honestly, I think this is just set from list x86 base dot caller save registers. Oh, we need to list map this with location reg. Yeah. Okay. So tail jump. I think this is the empty set, because what we do with tail jump is we are going to right, it's going to read from, we already handle reading from the argument registers, right? What does it write to? The problem is we will have, so the thing that will have initiated a tail jump is probably a regular call queue or an indirect call queue. And so we're expecting REX to be written to, but that's already handled. It doesn't need to be accounted for in the liveness. This is basically an empty set, just like jump is. And jump if. So I think that we do this. They don't say explicitly here. Okay. So we need to go back and fix, before we go any farther, we need to go back and fix this. So let's go over here and we're going to add the arity here. This is going to break a ton of code. So select instructions. Where are we generating indirect call queue? Oh, what's wrong here? Okay, the imported module has errors. Oh, it's that I haven't formatted it correctly. Arity. Yeah, we're going to ignore arity for now. Okay. So now here, let's go ahead and say arity, and we'll just pretend that it has worked. And we're going to do, gosh, I want to rename that. Rather than just A, it can be label. Actually, let's just do this and then join those clauses. Okay. Yeah, includes REX. Okay. Next version of Gleam will have an LSP action to rename those. Yeah, I'm looking forward to all the LSP improvements. Should be good. Okay, so now we need to go back here and find where the bug is. Okay, so the thing is, we just know it. It's the length of the arguments. Why did I think this is gonna be so hard? I was gonna be like, oh, we need to propagate the type. No, just like, that may be the only thing that we need to do. We're gonna break some tests with this, obviously, but I think that this is one of those things that is kind of weird about compiler development, is that you have to build up trust in the passes that precede the one that you're working on. And I think that if we had a case where we were trying to call a function with a different number of arguments or different types of arguments, that it wouldn't get to this pass. I think that that's pretty fair, right? So at this point we can say, if there's a call, let's see if there's anywhere else that indirect. No, this is the only place. The other places we use tail jump, right? And if we look at tail jump, tail call, function arguments, we use length of arguments. So I don't know why I left that off. I think I was having some doubts, but we may have just fixed it. And let's see what the test is going to be broken. Okay. So oh, it's just complaining about it can't build that phase because we are reusing those functions in build interference. Okay, so I don't think that we can, without like commenting all of this out, I don't think that we can deal with, is this correct yet? Because we can't run the tests. So let's go on to the next phase. So we compute a separate interference graph for each function. So let's go ahead and make that change over here. We're going to move. So we've already got the types on the definitions. We're just going to move all of this up here. And just for the sake of not making this harder, let's just do that. This change, I mean. And then, yeah, select instructions. Where are we doing? Yeah, select definition. So we need to do okay, so we're going to say definition, and then let's put these up in here. I need parens. Okay. So we need label. And this is just so that we can return l.int. Well, we'll say void. Types, blocks. Okay, blocks. Dict.new, types, dict.new. All right. This is so void t. And we will be overriding that anyway, so we can say new definition and then just splat that. So that saves us later. What's the warning? No, that's not a warning. This is a warning. Yeah, okay. So we can get rid of that. That's the only place it's called anyway. New program, bye-bye. We don't need you. And let's, oops, inline that variable. Easy enough. Love the LSP. It's so good. Okay, so now we've got the types. Now what we can do is go over here to build interference. And remember, like this transformation we're doing with our oh, well, first of all, I need to change this to def call q as x86. Okay, so now I need to say this is definition. We're basically doing the transformation that we did for each of, like for the original program on each function definition. So we're going to make this let me put a to do here, and then that will help. Okay, so this is what our return for building interference or the whole program is going to be. Okay, and then we're going to update this. So here we have def.types. So anywhere we have program, and we need to update this. This is lfun. Okay. Def.blocks. Okay. And then we'll say this is def, and then we're definition. Okay. So now the issue is we need to handle, let's see what's wrong up here. Yeah, typo. Okay. We need to handle the other instructions. Actually, no, we don't. We already handled it in Uncover Live because it really only relies on what are the read and the write locations. Yeah. Or what are the locations in general. Let's see what they have to say. Okay. Okay, recall in section 6.7 we discussed the need to spill tuple type variables that are live during a call to collect the garbage collector. Okay, so with the addition of functions to our language, we need to revisit this issue. So I think that's about this. So functions that perform allocation contain calls to the collector. Thus, we should not only spill a tuple type variable when it is live during a call to collect, but we should spill a variable if it is live during a call to any user-defined function. Okay, we're going to have to think about this more deeply because there's a lot of... This is a high-level discussion of what we need to do, but not in detail. So, okay. Thus, in the build interference pass, we recommend adding interference edges between call live tuple type variables. So these are, this is going the tuple type variables and the call save registers. Okay. In addition to creating edges between the call live variables, and the caller save registers. Okay, so I think that yeah, these rules are kind of dense. I say they're dense. There are a lot of semantics in a small amount of code. Okay, so this handles callee save registers just for the GC's sake. So I think this is really subtle because if something is tuple typed, we can't blindly make it have a conflict with a caller save register, because what if we need to pass that tuple as an argument to that other function? Hello, Kasai. What are we building? We are working through this book called Essentials of Compilation. It's written about a Racket-like language, and the examples use Racket for implementation, but we are doing the implementation in Gleam. And we are in chapter 7. So I've been doing this series, not contiguously, but for quite a while. You know, since, I don't know, January of 2025. So it's been going quite a while, and we've gotten pretty deep into the book. You see we're at page 155 of 239. So if you want to follow along with the book, you can go IU compiler course. This is the source of the book and the examples. And it's in LaTeX, but you can download a PDF of the book if you want to follow along. I also have the hard copy, but I stopped using the hard copy on the stream because it was like me looking down at the book and you can't see what I'm reading. So we switched to the PDF version. Okay. So again, this is not so much. Yeah, it is a really interesting project, and I've learned a lot, and I hope folks who have been following along or just joined recently have also learned a lot. Compilers are really interesting bits of code. So, okay. Right, so I think... I need to refresh my memory on what these rules mean. So we will go through the code. of each of these rules. And I want to see if one of them applies, or if we need to do another sort of patch up after the fact or before the fact. Okay. So what we're doing here is we're going through the types of variables that are in each function definition. So all the things that have been, I forget where we build this. I think it's during select instructions. Yeah, we're looking at, we build up the type definitions there. And this is, again, where I was like, oh, is this thing, do we need to track the function types as well? Maybe we do, we'll see. But for the basic variables, the ones that are not function references, we have all the types. Okay. Okay, so let's unpack this. We already know that we need them to be in conflict with the callee save registers, right? But we don't know if this vector is even live when we do a... Like, we have to look at the call site to see whether it is live to know whether we need to build a conflict. I'm wondering if this will fall out automatically. The other thing that we could do is yeah, let's look at rule 1 and rule 2, and then we'll determine whether we need to put another special case in here for instruction where it's a call, like either a tail jump shouldn't matter, but like an indirect call or a call queue, and then adjust, look at the live set and then compare the type, and if it's, vector t, then we add conflicts here. I think that that's what we should do. Okay, so rule 1, this says, okay, so we have the input is a graph, an interference graph. We have the live set, and we have the source and the destination. So in the case of, this is for like move Q, move ZBQ, we should probably put LEAQ in there as well. But interestingly, we didn't for the other things, like the other things that use globals. So that's interesting. Maybe we don't need to. Anyway, all right, so this says we have a set. This is the locations in, right, so we're moving from source to destination for moves. Okay. So we have a set of locations in the source, a set of locations in the destination. All right, so we make sure that we have all those locations in the interference graph. And then we fold over the live set. And okay, so we're modifying the graph, the input graph. If we have a location in the live set that is contained in the source, or if it's not contained in the source and it's not contained in the destination, and I've reused variables here in a way that's not great. Okay, so then we're saying if it's not using the source and it's not using the destination, then we're going to add a conflict for everything in the destination with that location. Right. So what that's saying, okay, let's unpack this rule again. What this is saying is if there's an element of the live locations, so variables and registers, that is not part of this instruction, this move instruction, then you cannot write to that location. So this is saying the destination cannot write to the live set. That seems pretty straightforward to understand. Okay, so the other bit is rule 2. So if it's not a move instruction, so rule 2 is what are the right locations? What things are written by this instruction versus the live set? Okay, so again, we're making sure that all those locations are in the graph. And then we're folding over the places that are written to by this instruction. And then we are folding over the live set, and we're saying that if these two locations are not equal, then they must be in conflict. So if it already writes to something that's live, then it needs to be in conflict. Okay, so that's a really simple rule. So I think the question is, do we need to make a new rule for this? Or do we adapt rule 2 or the preparation step? Okay, so maybe I'm tempted to make rule 3. The problem is it's like an extension of rule 2, right? So I think that what we'll do is we'll say this should only matter for indirect call queue. Or call queue. Okay, so we're going to make a special case here. Or is it already handled? Because we are... So this is already caller save registers, right? Write locations, caller save registers. So this already handles that if we just pass it along. Right here, we don't have the types. So we're going to have to pass that in. Oh, def.types. Really? Okay. All right, so we have the set of live locations. So what we want to do I think the interesting thing is I think that this. No, we're already creating a conflict between and the callee save registers. So maybe this is already handled. I mean, we're not checking whether they're live. I think that this is a bit of a hack, actually, because what we'll see here is like, this is indirect call queue. This is call queue, which could be a call to collect. So maybe we move this into here. What do you all think? I'm kind of on the fence because in some ways it looks like if Rule 2 already handles the write locations in an instruction, which over here we have said the caller save registers are written to in that instruction. So we've already covered the caller save registers. And the callee save registers are handled up here with this, are any of these things vectors? So maybe we don't need to do anything here. Although it feels a bit overly strict. Because again, the issue is, can we, do we get into a situation where we can't allocate or we can't map a tuple variable into an argument register? Because ultimately what we'd like to do is, if that thing doesn't need to move for the entirety of the call, like across the call boundary, but also in the things that precede the call, then it would be nice to have that get removed by the the people optimization we already have, which is removing redundant moves, right? So let's say you have an argument to a function, and and it's the first argument, and it's vector typed. So when you make the call, it's going to be put in the RDI register as an argument register. So we would like for it not to be spilled to the stack if it's just going to stay in RDI the entire time. So I think a blanket, if we look at what are the callee save registers, the caller save registers are include RDI. Yeah, I think that this narrows what we did before, because we only care about if they're live when we make that function call. So the thing is, the read locations. Yeah, and actually this look at this. There's an overlap there. Let's extract a function. And this is argument locations. Rename argument locations. And we can, sorry, I just saw this refactoring. I'm like, I need to, yeah, remove block and then convert to function call. Okay. So this again, this is a bit of redundancy. We can say this is argument locations arity. That makes me feel a lot better. Okay, so this is before we had user-defined functions, and we had to worry about the calling convention. We were able to do it blanket-wise because we only had two things that you could call. You could call the garbage collector. You could call the allocator. I'm sorry, so it's more than two things. Or you could call readInt. Excuse me. So that meant that yeah, I think we need to handle calls more holistically here. And I'm noticing a little bit different. So edges between the call live variables and the caller save registers. So that the read locations, sorry, not the argument locations. That's this, the caller save registers. So those are the right locations for a call or a call queue. Okay, so we need to special case the tuple type variables versus the callee. Those need to interfere with the callee save registers. But in general, the call live variables and the caller save registers conflict. And I think that we've already captured that bit here with rule 2. So the right locations for call queue are the caller saved registers. So rule 2 already handles the that conflict. So we're going to, we're going to go here. And I think that we're going to get rid of this special case. And we're going to, let's comment it out first so that I don't lose the essence of that. But we're going to fold def.conflicts there. Oh, whoops. What did we do there? Def.types, folded over that. Producing an interference graph, right? Oh, I need to reorder the arguments. Yeah, so this is the accumulator. Okay. All right, so we're going to here in call queue. We're going to start with G, and then we're going to do rule 2. How do we do this? I've forgotten how you do that. Name this thing while matching on it. It's not at. Oh, as. Yeah, okay. Okay, so now it's just complaining about that. Okay, so we're gonna do right locations. Okay, and then we're going to augment those with this bit. So call live tuple type variables. So we needed to say okay, we're going to take I think what I want to do is fold over the live set. So we're going to fold over live. G is going to be the accumulator. And then this is the location, G and the location. Okay, so G is the graph. So we need to go case location if it's a var, this is the one we care about. Here, if it's a register, we don't care. We're not going to modify the graph. Now, if so, if this variable is in, oops, if it's in the types and it's vector t, right? This is what we were kind of doing above. Okay, this is getting really very nested and I don't care for it, but we can figure that out later. Okay, if it's a vector type, then we already have that name. Okay, so what we can do is we can say add locations, and then we're going to say oh, it adds a set of locations. Okay, so we need to make sure that, well, rule 2 would have handled that liveness already. It's already added all the locations. Okay, so we don't need to add it again. I kind of wanted to be safe there, but we can add a conflict. We're going to do another fold. This is really messy. We're going to fold over x86 base dot call save registers. And we'll add a conflict. I wish I had added something that just, you know, takes a list or a set. Oh well. Okay, so we're basically doing what we did up above. We're doing this, right? Okay, and this is more general than what we had done above, but also more specific in that it's only considering whether the variable is live. Because if it's not live, then we can throw it in one of those call save registers whenever we want. Okay. I think that covers it. The problem is, this is like, how do we create a test case for this? I mean, I guess that what we'll do is we go over here to the tests and see what we can manage. See if this is correct. And that we already have in here in the interference graph a way to say, you know, are these two things in conflict? So that should be straightforward to test. So let's look at uncover live test, and we're going to uncomment things and address them. So this is going to be lfun. x86 global is going to be xdef call queue. We need to redo this. We're going to have to fix a bunch of things. You know, the other thing I think we didn't do is we didn't re-enable this. So, yeah, let's get to fixing things. And this is Lphone. This is x86 def call queue. That's x86. Okay, and we're gonna have a bunch of broken things. Hello, Gun 974. Sorry I didn't see your message. Yeah, I think that this is... and we're going to have to deal with this. So this is going to be a list, and this is actually x86.definition. This is blocks. Yeah. Let's adjust that. Actually, we're gonna say name is main. Okay, and we need to close that. Okay. Name label. Yeah, label main. Okay. So we can keep iterating through this, and we're gonna have to fix this as well, the C program. Just a list of definitions, so we can go like so. And I'm gonna have to look back at this. C fun. Okay. Name, arguments, return, blocks, body. Okay, so this is body. Name is main. Arguments, empty list, return type is L.integer_t. Oh, and we made the blocks special here. Oh, right. Okay, so that's not too hard to fix. Okay. Now we need to do this very mechanical transformation again. So I think what I'm going to do is try to copy prefixes of things. Apologies for not talking. Just kind of focused on this. You know, it's interesting. We have this C program with this like arbitrary dictionary in it that we don't use. And there's a bit of, in the book, some like, how to describe it, you know, this okay, c.blocks. There's a bit of trying to prepare for the future in a way that like is open-ended and is fine in a dynamic language, but in a statically typed language makes no sense, because you have to define everything. And like in Racket, you can make lists of arbitrary terms, and that's fine. And it just doesn't make sense in Gleam. So we have a bit of waste in here that I'm not really happy about. Okay. I think that we're going to find that some of this just doesn't work anymore. We're going to have to update the parsed and the pre-passes and all that as well in this test. And I wish I'd done that at the beginning, but it's okay. And again, my apologies for this being really, really tedious. Not great content. But we're pretty far down in the file. It won't take much more. Yeah, and I think this is the point at which I started to get to we care more about the end-to-end and less about constructing the individual IRs ourselves, and that was a big improvement. Okay, we don't need to change that. Ba-da-da-da-da. Right, and we should get rid of this should be okay, because we're not using that. We'll deal with that in a minute. Let's get this last one fixed, and I think that what we need is let assert. We need to make this into and that should fix that. Okay, so parsed, we're just going to copy from some of our other phases. So like, what came before select instructions? We did explicate control. So we should have that helper in here somewhere, down at the bottom. Yeah, okay. So we basically need to do this. That will be the parsed bit. Okay. Oh, we're just doing parsed. Actually not. I'm not concerned about that. Let's move that into here. All right, so this is input, and we need to make sure that we use these. Okay. We're going to have to comment out this entire module again, just because I want to make sure that we get select instructions passing. Okay, so we're going to have some things to address here. I wish those diffs were better. Yikes. But let's look at how they failed. Line 73. So this one, what did we get that was different? So here we've actually defined the C program. All right. So I think we need to drill down into not just a direct equality, but yeah, let's break it down. Okay, so what we define as the golden is on the right, and we call select instructions on the left. So I think that what we need to look at is, let's ignore the other bits, and I think that what we want to see is like what are the contents of the instructions, see where they differ. So move 20 x2, move 22 x1, move x2 to y3, add x1 to y3, move y3 to rex, jump conclusion. Okay. Do we just have an issue of something else? Like some part of the... because this does not, this will construct the interference graph for the base, but does not do anything with it. Okay, and we have x1 is integer t in both of them, x2 integer t, y3 is integer t in both of them. And then it's just a graph. So there's something here in the middle. Something there in the middle that's not equivalent. And I can't tell what it is. Does anyone have a good diff, like structural diff library? I guess what I could do is I guess we're gonna have to look at what's in the graph. So R10, R10, 6, empty set, R11, R11, -4, empty set. Yeah, this is strange. Like, okay, I think that what we're going to do is we're going to comment that out, and we're going to say I'm going to pull that out. I'm going to say let assert x86 program what we'll do is we'll do these assertions and then we'll restore the original. So and we're going to say label is main return integer t. That's going to be select instructions of the C program. And then we will do a dot on the end here because we don't care. So we're just, I want to make sure that the blocks and the types are the same, and we're not getting into, is the interference graph exactly constructed the same way? And we'll do equality on that and types. And if those are unequal, then we can see the problem better. Okay, so we're looking for an assertion failure on 86 or 88. We do have one on 86. So we have an assumption about where it's jumping to. It's that we are making the conclusion have a prefix on it. That's the fault. That's the issue. Okay, So let's unwrap. Let's undo all this. And we'll make this the assertion again. And get rid of this one. And this is going to be main conclusion. I'm such a bonehead. Sorry, folks. Okay. So we should no longer get a failure in that function. (112.208). Okay, so it's an issue mostly with renaming. I need to do all these jumps. They need to say main conclusion. So let's find conclusion and replace with main conclusion. Derp. Okay, let's see if it fixes those tests. Okay, we're down to 4 failures. There's some other issues going on. You really need those Yes, I know I need those snapshots. Thank you. Snapshots would be good. But I still want to make sure that I'm getting the little details correct. So I don't know if Birdie could just snapshot my these data structures directly. If I don't have to convert them to some other format, that would be ideal. I don't know. Heck, if they're like Erlang terms, that would be cool too. I'm okay reading Erlang terms. Okay, so let's look at 112. Let's see what might be wrong there. Oh, so we have a problem here in that I moved the type check. Yeah, let's do this. Because I think that what we did here was typed. We made some assumptions about the other thing I could do is just combine those two and not use the manual construction of the AST anywhere. Let's see if that resolves that, because it could just be that we're missing the type on something. No, it still fails. Okay, 112. At least I put it back the way it was for the most part. Okay, so we got, oh, main. This is a bit that I think I should go back and fix, and then this should become like main underscore start. Pretty print and Birdie. Let's look at pretty print real quick. I think that's an interesting idea. Ooh, look at the docs on that. Okay, print with style. Yeah, so it's a little small. So format just takes anything and converts it to a string. So that uses unstyled bit arrays as string, no labels. So the config, style mode, styled, unstyled. So styled we would probably want without ANSI codes. Label mode only affects JavaScript target, right? Okay. Bit array mode. Okay. pprint. That's interesting. Pprint and Birdie. That could help, especially if Birdie will show me good diffs that have enough context in them. Okay, so that was that problem. This one, again, I think that, no, we used start there, so that's not going to cause the issue. So here, this one, because we went from the concrete syntax, this is going to be main, not start. Kind of really made it hard for myself, didn't I? Here's another one. Okay, and we're not looking at what the names of the definitions are here. All right. Down to one failure. Okay. So let's look at, right, so it's select instructions tuple test. Line 320. Okay, so this block 1 does not exist in there. Let's look at the keys of this blocks. Let's see what's in there. Ah, right. So this is another case of prefixing where we need to go main block 1, main block 2, and so forth. Okay. Main block 1. Are we looking up any other blocks? No. Okay. We are back to actually working. All right. So 315. So I think that I did us a disservice of not fixing these tests last time, or at least not starting the stream with that before we started doing the register allocation stuff. But what we can do is let's add one or more tests to select instructions that covers the stuff that is unique in this chapter, right? So we need to think about these fun refs becoming LEAQ instructions. Fun ref becomes LEAQ. So we need something that exercises that. We need moving things to argument registers, to and from, right? So to on the calling side and from on the callee side. What else? Thank you, Willie, for putting in there, and I'll have a look at that. That feels like a whole 2-hour stream on its own, doing that conversion. I may even do it off stream just to simplify things. Okay, the other things are indirect calls versus tail calls, right? So we need to cover that. We need to cover capturing return values from RAX. Let's see. Those are most of the things that we need to cover. Can we do that in one test? Let's start with okay. Let's start with the example they give in this chapter that we've used a bunch, which is the, oh shoot, I went too far. Went way too far. Read table of contents. Okay. Where is that example? Fairly in the chapter. Here we go. So let's use this. All right. Okay, and we're going to say this is parsed, so it's a valid program, and pre-passes. Pre-passes. You can tell it's getting late in the stream when I'm like, Urgh. Okay, so this is our program. And I'm putting some returns in here so we can read it better. Okay, so what are the things, what are these things that we want to look at? So I think what we want to do is maybe what we'll start with is just echoing the result of select instructions. But we could do things like so funrefs turning into LEAQ. So we can say that map and inc in main are put into variables with LEAQ. That's some assertions we can do. Okay. And then when we call, so in main, when we call map, it takes 2 arguments. So map, the call to map in main receives 2 arguments. And the other thing that it says is there are 2 calls in map that receive 1 argument. Okay. And then we can say that main copies the result of calling map in a variable. And map copies the result of calling f twice into variables. Okay, indirect calls versus tail calls. This does not cover tail calls. Now, if we did map inc, that needs to be, I think that needs to be a different test, because what we would want for the tail calls so let's say select instructions tail call. So maybe we'll have a function or a program that looks like, let's just define ink like this. And this is going to be ink to 41, right? So this program what we would want to see here is that main puts ink into a variable, and main tail jumps or tail calls to tail jump, right? We say main puts, or we say ink puts one argument into registers before calling ink. No, main puts one argument. Yeah, it's getting late into the stream. Okay, so let's start with just, we're going to echo select instructions on both of these. And what we will do is kind of visually, this one's going to be harder. Let's look at, let's maybe comment out this one. And then we'll look at this one because this is a simpler syntax, a simpler program. Okay, so it's still a lot, right? That's not what I wanted to do. Here, let's just drop it down. Still fireworks going off. I don't know if that's happening to you all. Okay, so looking at main, we can say, yeah, we load ink into a variable. We move, so we move the argument into RDI. That's another thing that we can check. Then we tail jump to, you know, to whatever that was loaded into. Okay, and then let's go down and find where ink is defined. So there's definition main. Where's the next definition? That graph really makes it messy, doesn't it? Okay, here's the ink definition. So we move, so this is moving RDI out into X1, moving X1 into RAX, and then because it's return. Okay, so this is like, yeah, adding 1 to RAX because that's return. That's an interesting thing that it already decided that. We didn't do any register allocation, but okay. All right, so that's pretty reasonable. Let's make assertions about that. Okay, So we're going to do let's assert about, and this will be the last thing we do on stream, I think. And then I really hate that we're getting the tests and the code split up between two streams, but that's kind of been the pattern lately. So let's look at what main does. So we have blocks. I'll say main blocks. And we don't care about the graph, we don't care about the types. So what I'm just going to do here is say we're going to do list find on p.defs and that's d dot find takes a function and returns a boolean. So d dot name equals main. Okay, and then we're going to say let assert okay x86 definition blocks, and we'll say inc blocks. We'll do the same. Okay, so now we can say and we'll do the same for inc. Right, and we need to splat the rest of those. Oh, right, so we actually need to do, we're just going to pass this to select instructions because I'm not going to do full structural comparison there. Okay, so now we've got a block that is main. So now I want to we're just going to outline the instructions. I think that's the right thing. We want a pattern match on that without getting too detailed. So we know it's going to be LEAQ. We're going to say ivar. I don't actually know if this is going to work, but we're going to say main.body. x86 dot move q immediate 41 into x86 dot register RDI. And then it's x86 dot tail call inc ivar. Yeah, I don't know if you can pattern match this. It probably doesn't work. Duplicate variable. Okay, so lvar f, we're going to say lvar fvar and say if lvar equals fvar. You know, the other thing I can just do is say, I know it's going to be temp 1. I think that's probably the easiest. Because there's going to be only one temporary variable done there. Okay, this is tail jump. All right. Well, let's see if that passes. Okay, it's not name, it's label. Need to be really more consistent, but sometimes they use words interchangeably. Where's my echo? 449. Oh, it's in the past. Oh yeah, this is a case where you have a tail. The type is unknown. I don't know why I had that echo still in there. So okay, so we've got that. Let's finish out these assertions. The other thing that we could do is go like, let's not, let's call this lvar, and we'll say let assert, and this is fvar, and then we can say assert lvar equals fvar. That's probably better. And then now the ink, so we said puts ink into a variable, puts one argument into registers, right? And it tail calls. Those are the things we wanted to assert here. We know it's going to jump to the conclusion. Let's look at, okay, so what else was it going to do? We know it's going to move. It's going to move from RDI, which is the first argument, right? Actually, it's just reg. Into X. And then we know it's going to this is going to be RAX. So what we want to do here is we want to assert x equals x1. Really, we're just talking about how it's breaking up that add instruction. And then let's test that and see if it passes. Okay, so this is a bit less prescriptive about what things actually are. It's just we're concerned about data flow here, and that we are loading registers with arguments to functions before we jump or call, and so forth. Okay, this is a good place to stop. Let me have a look at your example there, Willie. Right, okay. Mm-hmm. Cool. That's good. Thank you for that. What I might do off stream is take some time to look at whether I can convert some of the more significant tests to birdie snapshots. I think the challenge with that is a lot of every time we make an enhancement to this and we change the snapshot, we need to make sure that we can manually verify those changes. And if it's too complicated, then what happens is you tend to get concerned with details that don't matter. For example, like one of the big things that this test does versus what I was doing in the previous tests is like we've got those pre-populated graphs because they need to be on that data structure, but they're not relevant to the thing that we're trying to assert over. So it gets kind of messy, and I want to avoid getting too messy there. Now, what we could do is say, like, pull specific things out and snapshot, for example, the blocks. That would be okay. That would be good. Maybe we'll do that. But this one, I think. Yeah. All right. Thank you all for hanging out. This is not easy stuff, and we'll get further into it next time. Next week should still be a normal stream week. I am traveling the following day, but I don't think that it'll interfere with my ability to do a stream. So we'll see you next weekend. Thanks for hanging out.